right, we're going to look at section 1.5 on tables. But really, the big concepts here are this thing called the IVT, which stands for the Intermediate Value Theorem, and average rate of change, which I will commonly abbreviate AROC. In IVT, we obviously abbreviate IVT. These two ideas are so important for what we do this year that I know you learn about average rate of change in Algebra 1 and then again in Algebra 2, but it's a really big deal. So first of all, I'm going to assume that you have read this text. If you haven't, pause the video and read it real fast. I'm going to jump into this first example, and then we'll spend a little more time talking about IVT on the next page. So let's let this function w of t be a continuous function. It's going to be important to us. That models the amount of water in a reservoir at any time t. And then we're given these parameters between 0 and 20. So we could treat that like a domain restriction on t, where t is measured in hours and w is measured in hundred thousands of gallons. So w is a volume. Selected values of w are given in the table below. When the outlet gate is open, the volume of water in the reservoir is decreasing. So if more water is flowing out than flowing in. And when the gate is closed, the water is increasing. So when they open the gate, they're letting more water out than what's coming in, is how I'm interpreting that. Okay, so this is going to start off like something we did in our very first lesson this year. So evaluate w of 7. Using correct units, explain the meaning of w of 7 in context. So when we evaluate w of 7, oh, gross, Boomer. Sorry, my cat just shook like something wet on me and it was gross. All right, when we evaluate w of 7, I'm just going to look in my table and there it is. W of 7 equals 12.9. When I evaluate it like that, I don't need to include units or anything. We're going to do that next in this next part. So using correct units, explain the meaning of W of 7 in the context. Well, we said that W is represented in the units of hundreds of thousands of gallons. And we said the function W of t models the amount of water in the reservoir at any time t. So W is amount of water in the reservoir, and the units are these hundred thousands of gallons. And then we know t is time, so the t value is going to be a time, and it's measured in hours. Those are our units. So to interpret this in context, we could say at time t equals 7 hours, then we want to describe W. So we would say the amount, I'm going to abbreviate amount, of water in the reservoir. I won't ever count you off for spelling, but the word is spelled right there. The amount of water in the reservoir is 12.9, and then we said 100,000 of gallons. Just to avoid, hold on, let me write this first, 100,000 gallons. To avoid a silly mistake where you try to write this out as 12,900,000 gallons and you expand that number to get rid of the decimal, that's fine if you do it correctly, but I would just write it this way to avoid putting the wrong number of zeros, if that makes sense. The other thing I would be really careful about is make sure you don't use a word like after. So if you catch yourself writing after 7 hours, that really means after 7 from 7 to 20 in this context. So anytime we're talking about an instant in time, I would encourage you to use the word at. And I know this is not like a sentence that you would write in an English class. It feels very mechanical. That's fine for our purposes. We're not creatively writing right now. All right, next we have to evaluate W of 13 minus W of 10. So again, for that evaluate piece, the first thing I'm going to do is just the literal math. So W of 13 is 16.2. W of 10 is 14.8. And I should be able to do that without a calculator. I think I've told you by now that I'm pretty bad at subtracting in my head, so I'm going to actually do this out to the side. So we get, what, a 4 there. 12 minus 8 is 4. All right, so we get 1.4. So W of 13 minus W of 10 is 1.4. And again, when we evaluate, we don't need any units. We're just going to write the numbers that we get. Using correct units, though, explain the meaning in the context of the situation. So anytime we subtract, really, this is a difference. And that's a word that we could use as we're explaining this in context. So we know that at time t equals 10, the water was 14.8 100,000 gallons, the amount of water that is. At t equals 13, we could think of this as the difference, or I could realize too that it has increased from 10 to 13. But what we're looking at is how it changed. So we could say between times t equals, and we're always going to move time forward. So even though it was W of 13 minus 10, I'm going to say 10 first. So between times t equals 10 and t equals 13, I'm going to include my units, hours. All right, so now we think, what has changed? Well, it's W that's changing. So the amount of water in the reservoir. And then the question is, how did it change? Did it increase or decrease? Well, if I look in my table, I can see that it increased by 1.4. So between times t equals 10 and t equals 13 hours, the amount of water in the reservoir increased or increases or is increasing. The tense doesn't matter. I'm just going to say past tense. Increased by 1.4, and then I need my units. 100,000 gallons. So 1.4, 100,000 gallons. Okay. When the volume of water in the reservoir is 1.25 million gallons of water, an alert is sent to Denver Water. What is the fewest number of alerts that could have been sent in this 20-hour period, and explain how you know? So this is where the units get a little bit tricky. 1.25 million. So like if I think about this, 1.25 million is going to be the same as 12,500,000. So we just move that decimal place back one, and that's 12,500,000. I'm not loving the change of units in this problem, but whatever, it just makes us think harder. So if we think about it, going back to this phrase that I highlighted at the beginning, we were told that this is a continuous function. So meaning there's no discontinuities. So what I mean by that is we can't jump from 15.1 100,000 down to 12.4 without passing all those volumes in between. So the function, like if we were to look at a graph of it, wouldn't have any discontinuities. So I want to think about how many times must we cross this 12.5 100,000 threshold. So I'm going to look at the table, and just for ease of it, I'm going to delete the stuff that I wrote on the table. I know if you're writing at home with me, you can't really do that, but it's okay. So I could see that at some point right here between 0 and 2, and I don't know when, but I would have to cross that 12.5 100,000 threshold to be able to land at 12.4. Now I'm going to cross it again between 2 and 7. And it looks like, and I'm reading this problem again, it says when the volume of water is 1.25 million gallons, which we said is 12,500,000 gallons, when that's the volume, an alert is sent to Denver Water. So it doesn't say that when we drop to that volume or below, it just says when it is that volume. So I know somewhere between somewhere between t equals 2 and t equals 7, I'm going to have to hit that 12.5 mark again. So we could assume that there's at least one instance in between where it goes to Denver Water. Now, we don't know what's happening between 2 and 7. It could be that we're going up and down a bunch between 2 and 7. I don't know that the amount of water is always increasing, but I know that to get from 12.4 to 12.9, if the function's continuous, we're going to have to pass 12.5 again. All right, between 7 and 10, we don't know what's happening. The water could always be increasing. Between 10 and 13, same thing. It could be increasing. It could tip down. We don't know. But what we do know is that there must be another time between t equals 13 and t equals 17 where the amount of water hits 12.5 because it decreases from 16.2 to 10.5 hundred-thousand gallons. And then again, we don't know really what goes on between 17 and 20. So where the question is, what is the fewest number of alerts that could have been sent? The fewest number of alerts is 3. So I could say the fewest number of alerts sent to Denver Water, I'm not sure that was faster, is 3 alerts. And then when we explain how we know, well, what we know, I'm going to say because we know that W of T must equal 12.5 between T equals 0 and T equals 2, T equals 2 and T equals 7, and then lastly between T equals 13 and T equals 17. And again, the other big key piece of information here is that W of T is a continuous function. In this last part of the problem, we're finding the average rate of change at which the volume of water in the reservoir is changing between t equals 2 and t equals 10. So average rate of change really is just finding the slope between 2 points. So I want to plug in W of 10, which is what, 14.8, minus W of 2, which is 12.4. You must always show your work for this. This is called a difference quotient. So when you're finding the average rate of change, you need to show me first this top line, then the second line. That's just like an AP grading convention. All right, 14.8 minus 12.4, that should be 2.4. And then we know 10 minus 2 goes to 8. So we get 0.3 or 3/10. And we will spend more time later on how to interpret that with units. But for right now, that is our average rate of change.